Number 4. Box slides down a frictionless ramp 4 meters long and inclined at 30 degrees above the horizontal. If it starts from rest, what is its speed at the bottom? So we're really well equipped to solve this using the methods that we learned way back in the unit on inclined planes. We could resolve the force of gravity into components, find the acceleration of the object down the ramp, and then use kinematics to find its speed. But this is actually a nice problem in that we're going to see the utility of this work energy approach and how actually nice it can be, especially in the right kind of a problem. So to solve this problem, I'm going to maybe start just with a quick sketch here to realize that I can calculate the height of this object. It's 30 degrees inclined. The object starts up here somewhere. And if I'm measuring from the bottom here, where I'm going to say that it ends up h prime equals 0, then the height of this object, h, is something that I can calculate based on the fact that I know the ramp itself is 4 meters long. So a quick trig calculation would reveal that the sine of 30 degrees is equal to opposite, which I'm designating the height, that's not the hypotenuse, that's the height h as shown in the diagram, over the hypotenuse of the triangle, which is the length of the ramp, 4 meters. So that means the height that it starts with is 4 sine 30 degrees. I don't need a calculator for this one because sine of 30 is exactly half, so 2 meters. Okay, so it starts at a height of 2 meters. It ends up at a height of 0, h prime 0. It started from rest, v equal to 0, and what we're trying to do is find how fast that it arrives at the bottom of the ramp. So, applying conservation of energy is going to play out just like it did in the last couple of problems. The ending energy equal to the starting energy plus the net work done by any non-conservative forces. Had there been friction on this incline, I would have had more to say about this network NC, but being frictionless, the only forces, in fact, just to point this out here, the force of gravity is, I'll just say, exempt, as I have been. The reason it's exempt is we've already got gravity figured out in the gravitational potential energy aspect. But just to be clear, there is a normal force. As a rule, it is not exempt. But in this case, the normal force does no work. And the reason for that, just to give a quick thought here, is that the normal force is a force that is perpendicular to the motion. And if you recall the work equation, it is the force times the distance cosine of the angle. I use the Greek letter beta to represent that angle between the force and the motion. The cosine of a 90-degree angle is 0 degrees. So any force that is perpendicular to the movement does no work. So in this case here, just to kind of go back up here, I can legitimately strike this term out. There were no non-conservative forces that did work. But just to be clear, there actually was a non-conservative force present. It just didn't meet the conditions of doing work because it was perpendicular to the motion. Okay, so just to continue along here, m prime, the kinetic energy that you end with plus the potential energy you end with, equal to the kinetic energy that you started with plus the gravitational potential energy that you started with. Striking out the things that I know to be 0, we end up at the bottom of the ramp where I'm designating height to be 0. We started from rest. So once again, we have 1/2, go back to my black. Once again, we have 1/2 mv prime squared equal to mgh. M divides out, as it so often does, and that means that if we are looking to solve for v prime, once again, it's equal to the root of 2gh. That's actually the exact same result from the last problem, by the way. And it just goes to show that this inclined plane actually didn't really affect the outcome. Kind of interesting, because if you had just dropped this box straight down to the ground, in other words, if there even wasn't an inclined plane present, the speed that it arrived at the ground would be the same either way. That's kind of neat. And this energy analysis really helps to see these things. Okay, root of 2 times 9.8. The height itself was 2 meters. I calculated that above. So that means the speed that we arrive at the bottom is, wait for it, root of the following. Okay, 6.26 meters per second. And I leave it at that for number 4. Problem solved.